Thanks, Ulf, and thanks for reminding me who I am, because I woke up this morning in this body and I'm not really sure what to do with it. I seem to be at ICFP giving a talk, and this like a whole Emacs buffer full of stuff, and I hope whoever wrote it has left me enough clues so I can give their presentation. I'm very grateful to be spending the summer at Microsoft in Cambridge, but usually I'm at Strathclyde. But yeah, anyway, better get on because it's it's a short slot. So I thought, since I'm basically going to program until Ulf bottles me off, so I better do the conclusion now. The message straightforwardly is types. I don't know why I use $signs for that. It must be the company I'm keeping. Yes, that's what I'm planning to do. I'm going to push types. And in particular, I'm going to push types into expressions. I'm going to show you the value of type checking and types up front as a way of structuring programs and the programming experience. Because at the end of the day, I want no, that's a mistake. I want to type less. And the other thing I resolutely set out to do in this talk is to prove nothing. Right. Lots of you think it's really great to be good at proving things, but I think it's even better to be good at not proving things. So, okay, what am I not going to be proving things about? I'm going to be not proving things about structures with some kind of ordering invariant. So let's contemplate the binary search tree. And indeed, it sometimes helps to think about these things lying down. And from this distance, I can kind of see the leaves and the nodes of the tree more clearly than the branching structure. So they're kind of falling towards me. And I can see that in between the data, in between each piece of data, there's a leaf. I think that's kind of useful. Never mind what the actual branching structure of the tree is. Still, we have this alternation: leaf, node, leaf, leaf, data, leaf. So that's some useful structure that's independent of the way the tree forks. We've got always a leaf between each piece of data and a leaf on either end. Okay, now let's also think about how we would write a type for search trees maintaining the ordering invariant. The crucial thing is to think about requirements. Right? If you start by asking the question, what can a type tell us about, what can we learn about, what type can we synthesize for a binary search tree, you'll come up with the wrong thing. If you think instead, what are our requirements of the binary search trees, then you'll discover that you can get just what you need rather more easily. So the crucial thing about binary search trees is that the data in them are ordered and within a particular range. And at the top level, we don't really care. We have no conditions on the values, which is the same as saying that we're happy if the values are between minus infinity and plus infinity, or bottom and top as I call them here. And then as we work our way through the structure of the tree, the keys that live at the nodes act as refined bounds for the subtree. So the 6 at the root is the upper bound for the left subtree, lower bound for the right subtree. And that works all the way down to the leaves. We can use the data at the nodes to refine the bounds until we reach the leaves, and when we reach a leaf, we know what ordering evidence we need. So the plan is store the numbers, or the keys that, in the nodes, and store the evidence that they're in the right order at the leaves. And because there's a leaf between every two keys, we'll keep the neighbours in order. We could instead index search trees by computing their extrema, but that gets us into a world of pain. And you know, I have a thing about pain. I have a condition. It's called cowardice. Okay. I also, as I'm going to, well, I actually am going to prove things, but I'm going to keep them invisible. And the way I'm going to keep them invisible is with this handy type called, so proof of T is a record type which has a constructor bang, and it has bang has one argument which is implicit, but it's not implicit in the figured out by unification Milner way. It's figured out just by hoping there's one of those things lying around. So okay, let's a helpful hint to myself. Yes. So for example, because this is really live actor, if we say, what's the goal here? Sadly, we're losing the left side of the screen, which is a bit annoying. Maybe I should. No, I'll not mess with it. So if I say, do case analysis on A and B, I discover they're both bang. But what's happened when I do case analysis is that the hidden proof has been unloaded into the context. I can't see it, but it's sitting in the context. Let's look. Oh, it helpfully doesn't even show it because it's so hidden. I'm so glad Ulf is the session chair, because if anything goes wrong, he can just fix it, right? Yeah, and then to finish the job, I just say bang, and because the right thing is lying around somewhere, it just works. Okay, so what are we going to have evidence about? We're going to have evidence about ordering. And the crucial thing that we'll need to keep our neighbours in order is that any two keys can be put in order one way or the other. And that property I describe, so it's a property of predicates. An ordering predicate is Owotto if you can get a proof of it one way around or the other. Some people call it being total, I suppose. And then, so that I define that as a sum of two proof types, and then I use pattern synonyms to hide even the occurrences of the bangs. So you're not even going to see the thing that hides the proof. And then I'll parameterize the whole construction over some set and an ordering relation and a proof that it holds one way or the other. Okay, step one, glue on bottom and top elements, because not every set has a convenient extreme values, and lift the ordering to include bottom and top. Next up, well, you see, my father told me it's just not worth solving one problem. Solve them all. So I want to explain how to put ordering invariants on all the data structures, or at least plenty of them. So I started with this. This is the polyp universe of Janssen and Göring, which explains how to make containers by describing their node structure, and you give placeholders for recursive subnodes. That's what the R is for, and then the P tells us where the elements go, and then we can tie the knot. So each one of these elements of U describes the node structure of an inductive data type, and then this mu is the data type itself. What we do for each unwrapping of the constructor, we deploy the functor that's been described by the code. Now I'm not going to do the ordering invariant for this universe. That's the key observation is that what makes the invariants easy to manage is the fact that every time we have two structures beside each other, there's a convenient key in the middle which acts as the upper bound for the left substructure and the lower bound for the right substructure. So what I'm going to do is I'm going to glue the P to the star. So I start by defining what it is to be two ordered structures with a thing in the middle. So that's what this hat is. So an S hat T between L and U is, first of all, it's some element of P, and then I've got an S between L and P, and a T between P and U. So it's a pair of an S and a T with a thing in between. And that's the pattern that always allows me to keep pushing the bounds inward. So I get this universe, and instead of having a separate P and star, I now just have the hat. So that's my universe, and I interpret the hat code as the hat operation, and I tie the knot in exactly the same way, except that instead of defining a set, I'm defining a set indexed by a pair of lower and upper bounds. And crucially, at the leaves given by the unit type, instead of just requiring boring stuff, I require a proof that the ordering relation holds on the given pair of bounds. So we have the general pattern of having data in between substructures, and at the leaves we have the evidence that shows that the neighbours are in order. So we can give codes for lots of our favourite data structures. So the first up is a completely non-recursive data structure. You can see the R doesn't occur in the code. I'm just saying that I've got a one hat one means that there is a single element stored between two pieces of ordering evidence. So that's just to say that packs up a single value in the given range. For binary trees, then as you might expect, I say, well, you either have a leaf or you have two recursive substructures, two subtrees with a key in the middle. And I can get lists by doing the same sort of thing, except I basically say a list is a right spiny tree. So it's either a nil or a cons, which is given by a key between something that's definitely leaf-like and a recursive sublist. Is everybody cool with why these codes describe these familiar data structures? And let me just, I've got a hint here that I should search for a keyword. Maybe that will work. Right, and if I make that alive, I've got a hole with an interval between 3 and 7. What number shall I put in the interval?
4, 8.
It won't let me put it in the interval. I'll have to put 4 in instead. Okay, so that's the way it goes, and you can see I've used pattern synonyms to try to pretty up the representation of the specific data structures that I've built with this coding system. I don't want to keep seeing all of these artifacts of the encoding. I just want to see the leaf and node and things like that, and I've even put the P in the middle. Just because it belongs there, even though the types of even though the type of LP depends on P, P still belongs morally in the middle. Okay, so 5 minutes to go. Can I write some programs? Well, clearly we're going to want to write insert, and I can do a case analysis, and I get shown all sorts of disgusting artifacts of the encoding, so I'm just going to write it by hand as quickly as I can. That's an error. And what happens? Well, we have a leaf or node LPP PU. And then here we want to give back node leaf X leaf. And here, well, at this point we probably need to find out whether X is greater or smaller than P, so that's fine. I do that with one way, no bar here, one way or the other. And I match on the result, it's either less than or equal to. I'm having to type too much code, but only because I don't want to show you encoding artifacts. And then here, I can try and make the standard undergraduate error of just inserting X in the left subtree, but it doesn't type check. If instead I actually remember to reassemble the rest of the tree around it, it does type check. And here, the other way around. And you'll notice that I'm unpacking an element from an interval and packing it up again into a tighter interval. There should be a closing parenthesis there, and a P in there, and that's good. And let me just bring the other things into scope while we're about it. So what happened? The evidence that told us we could insert X into the left subtree, well, crucially, we already had that X was above the lower bound, but just in time to insert X into the left subtree, we discovered that X was below P. And that's the other condition for even being allowed to do that. Yeah, the testing is generating the evidence that we need to do the operation and to establish the invariant that we're trying to achieve. Okay, I've also defined, so concatenation of these ordered lists is rather difficult, but concatenation of two lists with an element in between is just what we need for flattening, and it's very easy to define. So that I spent ages trying to figure out how to define concatenation of these ordered lists before I realized it was difficult because I was doing the wrong thing. It's a real case of you can't always get what you want, but if you try sometime, you just might find that you get what you need. And that sort of Jagger-Richards thing happens all the time with dependently typed programming. I'm going to skip this section. Sorry, Jenny, but indeed, we can indeed get rid of the quadratic flattening algorithm by being slightly cunning. Because I want to get to the indexed variant to show you one last thing. This is the indexed version of the same universe, because as well as imposing ordering invariants, I want to impose all sorts of other stuff as well. And the change is very simple. All I say is, well, instead of explaining how to make one sort of thing, I'm going to simultaneously explain how to make I sorts of things. So in a recursive position, I need to say which of the available sorts of things goes there. And then I need to explain the node structures for all I of the things. So I write a function from I to descriptions. And that way, we explain all the different kinds of things that we're making, and we tie the knot in the same way. And then we get back all the old stuff that we had by choosing the index set to be the unit set. So we're making, only one thing in each case. But we can also do more fun stuff. For example, here, defining 2-3 trees. So here I do an honest-to-goodness case analysis on the index of the type to see whether it's 0 or a successor. Right, now, the usual data type declaration notation doesn't let you do case analysis on the index. But the underlying possibilities of universe encodings do let you do case analysis on the index, and I'm exploiting that here. I'm saying that a 2-3 tree of height 0 had better be a leaf. However, a 2-3 tree of a successor height, well, we're certainly going to get one subtree, and then we're, to the right of that, we're either going to get one subtree or two. So we end up with these two pictures here. Either we have a node with one key and two subtrees, or two keys and three subtrees. And I can tell I'm out of time. I want to show you one moment of insert. So we're at the point where we have to compare the element with the pivot, and let me see if I can get this to work. It's fairly hideous, and I've got lots of encoding artifacts which I don't have time to get rid of. But in this case, we know we need to go into the left subtree. So we say with the result of inserting x in LP. So we'll get LP prime back. Okay, so the crucial thing here is that when you insert into a 2-3 tree, it either, if you're lucky, it comes back and it fits. If you're unlucky, it's slightly too tall when it comes back. So we have to look at what comes back. Ooh, why is it moaning about that? That's a nuisance. This wasn't in the script. Right. So if I look at that, I get two cases. And then what happens here is I say, dear Agda, what can possibly go here? And it says, two things can go here. This tree I can build, or that tree I can build. And since the second one is the one I started with, I know I want the first one. So it just fills it in for me. So that's the message I want to get across is, oh yeah, there's a computer. There you go, Wolf. Okay, so that's really the point there, is that because there are only two trees you can build with those data, the original tree and the correctly constructed rebalanced tree, bothering to put the invariants on the structure actually forces the program to be what it is, pretty much. So you're traveling with, in a strange gravitational field that sucks you towards the right answer. Of course, it can equally well suck you straight into the wall if you haven't spent 15 years figuring out how to write the definition that's just so. So, I guess maybe I've made it look easy and clean. It may not be God's immaculate machine, but if it makes you think about all the extra moves you make and the herky-jerky motion and the bag of tricks it takes to get you through your working day, then it's perhaps worthwhile.
So that's been fixed. So we have time for a couple of questions. Please approach the microphone. Dominic from Cambridge. Thanks very much, Conor. That was really cool. I heard you say this before about pushing requirements in, and I still don't understand it. So could you maybe sort of explain it to me just briefly again? Because I think the programs I write in Haskell don't push the requirements in. So.
Right. Well, if we go back, I think the picture is. Play my animation down. Yeah. So the point is that rather than constructing types for these trees which measure what's sort of the observable properties of the tree, right? If we wanted to, we could say, oh well, we can look at this tree, the left subtree, we can see that it has 1 at the left and 5 at the right, and we could use that to state the invariant, that the maximum of the left subtree has to be lower than 6. We could phrase it in terms of the extrema, in terms of measurements of the extrema of the trees. That's to say, the things we index by are quantities computed by bubbling information outward. But what I'm doing instead is starting from the requirement to be between bottom and top, and instead maintaining the sort of minimal conditions to push to get the right thing, just what's needed to make the left subtree okay. So that needs to be between bottom and 6. So the information that's driving the maintenance of the invariant is coming from the outside and being pushed inward, rather than being computed from the data. And that generally, yeah, I mean, it really is. It's the Jagger-Richard thing. You just say what you need. If you think about what you need rather than looking and measuring exactly what you've got, it gets simpler because it is simpler.
Excellent, that's very helpful, thank you.
Thank Conor again.